Let me talk a little bit about something called torque equilibrium. Sorry about that. The idea of torque equilibrium is that an object is in torque equilibrium if the sum of all the torques is zero. That is, if we add up all the twisting forces, that adds to zero. Now, in order for it to add to zero, of course, we have to have some convention here. And so this is our convention, is that, and you could do it the other way if you want, but let's just say clockwise torques are positive torques and anti-clockwise torques are negative, right? So let me just give you an example here. Let's suppose we've got a beam here and we've got a hinge, right? And I've got a bunch of forces, like maybe I've got a force here and a force there and a force here, right? And maybe a force here. Okay, if these are all forces, if that's the hinge, okay, all of these torques are, if this thing's in equilibrium, all these torques add to zero. Now, notice that torque right there is going to tend to rotate this anti-clockwise, right? So we would say that its torque is negative. So whatever this R is and whatever that F is, we would go negative RF. And since it's 90 degrees, a lot of these are 90 degrees, the sine of 90 would be 1, right? This guy here is actually about that point. Okay, we always have to have a reference point, right? This would be a clockwise torque, right? So we'd say it's positive, right? So whatever this R is and whatever that F is, right, this would be positive R1, F1, right? Where this is some F, right? This is F without a 1, right? Okay, and then this guy here, this would be a negative or an anti-clockwise torque. This again would be a positive torque. That is, this force acting all by itself would tend to make this whole beam rotate clockwise, okay? This force acting all by itself would tend to make the beam go up, which would be anti-clockwise. The same with this one, right? So when we say clockwise and anti-clockwise, basically torque equilibrium is saying that all the clockwise torques add up to all the anti-clockwise torques. Or if we make anti-clockwise negative, we add them up and they are zero. Okay, they all add up to zero. Okay, so let me just do an example of this and then I'll just post a bunch of other examples. I think you'll figure it out. It is, it's a little bit complicated, but it's not too bad. All right, so let's go. Here's an example, right? This is our hinge. Okay, so the first thing to do is you have to pick a point to torque about. Now, if there's a hinge, that's a good place to put the torque. Okay, now we'll talk about this a little bit later because you can pick any point you want. It's just that in this case, of course, we know how far these things are from that hinge, and so this is an incredibly convenient spot. But we could as easily torque about this point here or this point here, or we could go to the center of gravity of the beam. It doesn't matter, but this one's pretty convenient. Okay. So step one, let's pick a point to torque about, right? I'll torque about that later. All right, so we pick this point here. That's step one, right? Step two, express all torques, plus or minus RF, plus or minus RF, plus or minus RF. In this case, there will only be two torques, right? They all add up to zero, right? And positive torques are clockwise and negative torques are anti-clockwise, right? So let's look at this torque here, right? We've got an R of 2.15, a force of 5.25, right? And this definitely, if this force were acting all by itself, it would make this thing rotate clockwise. So this is a good upstanding positive torque, right? This force all by itself, about that hinge point there, right? That force would tend to make this thing rotate. It would lift that beam up. The beam would be rotating anti-clockwise. Okay, so this is going to be a negative torque. So when we set this thing up, remember, torque is RF sine theta. These thetas are both 90 degrees, right? Okay, so the sine of 90 is 1, so we don't need to worry about the sine, right? So for our torque equilibrium, I'm going to say positive 2.15 times 5.25. Okay, and then I'm going to say minus 5.82. Right, and what I'm doing here, this is R times F. R times F, and then of course this F we don't know, right? So that times F, and then that adds up to 0. All right, so this clockwise torque minus the anti-clockwise torque adds to 0, right? And then now we can do math, right? So we've done this, we've done that, right? And now we're on the step of do math, right? So 2.15 times 5.25 divided by 5.82 is 1.939. So force, right? Now this is some kind of lever. I always forget it's the first class or second class, or maybe it's a tenderfoot lever or something like that, right? Anyway, and I forget which kind this is, but it's kind of interesting here, right? I can exert a force of 1.939 newtons here, right? And it would counteract a force of 5.25 newtons here. So it's a bit of a force multiplier, right? Obviously, the closer this other thing is to the fulcrum point, the more force we'll get, right? And then what else? No, there it is, right? Okay, so anyway, that's the way that works. It turns out that you can set up torque about any point here, okay? This gets a little bit complicated because in reality, right, we know that this is 1.939 newtons, right? So therefore, there's actually a force down here of 5.25 plus 1.939. Now, the reason we know this there's a force of about 7.189 newtons, is that the forces up and the forces down have to add up to 0, right? This is what, if this thing's in equilibrium, then they have to, right? So this force is 7.19 newtons, okay? But we didn't know that coming into this, right? But since we picked that point to be the torque point, remember that forces that act right at the torque point have no torque, right? Because torque is RF. If R is 0, that is, the force acts right at the hinge, then it exerts no torque, right? So basically, the strategy for torque equilibrium is that you pick a spot, either it's a hinge or a spot where there's an unknown force acting, and then that force no longer is in the equation. You'll see this. Let's just put that in the back of your mind. Well, that'll be important later.